Hello everyone. Today I will present our paper titled Incorporating Embedding Vectors from a Human Mean Opinion Score Prediction Model for Monaural Speech Enhancement. The authors are Khandokar Md, Nayem and Donald S. Williamson from Department of Computer Science, Indiana University. I, Khandokar Md, Nayem, will present this paper in INTERSPEECH 2021. Let's begin. As introduction, monaural speech enhancement is a challenging problem that aims to remove unwanted noise from a target speech signal. For example, we are in a restaurant where many people are talking, music is playing too. A monaural speech enhancement system captures all these sounds using only a single microphone. The captured sound is called noisy speech. Then, speech enhancement system outputs the clean target speech by removing unwanted noises. Now, speech enhancement systems target maximization of speech quality and intelligibility measured by various proposed objective functions. However, current speech quality objective functions are often not strongly correlated with human subjective evaluations. In practice, it is often seen that speech enhancement systems report high objective scores but yield poor scores with a listener's evaluation. Now, we talk about some notable speech objective functions. Short time spectral amplitude mean score error STSA MSE is proposed by Efferham et al. In 1984 for the task of speech enhancement. This MSE style objective function is most common in deep learning models. However, MSE tends to produce over smooth problem in NS speech. Next, short time objective intelligibility STI, which is proposed by Tal in 2011. This is a popular metric for compute intelligibility performance of a speech enhancement model. In 2018, Fu et al. Jointly optimized a speech enhancement model with STI and SMSC as objective function, which improves speech intelligibility according to the objective and subjective measures. In 2018, Zhang et al. Apply gradient approximation and Koizumi et al. Use policy gradient method where STI is the objective function. In 2019, Kohlbeck et al. Compares MSE and STI as loss function. They suggest that applying the traditional STS-MSE estimator leads to similar gain of STI estimator. Next, perceptual evaluation of speech quality test is proposed by Briggs et al. In 2001, which is a popular metric to compute speech quality of a speech enhancement model. In 2018, Fu et al. Report that PESC does not improve when optimizing with STI. In 2018, Martin Donas et al. Proposed a PESC-inspired objective function that considers symmetrical and asymmetrical disturbance of speech. In 2018, Fu et al. Formulates QualityNet model for non-intrusive PESC estimation, which is used to enhance speech as a maximization criteria in Fu et al. 2019 and as a model selection parameter in the Rio et al. 2019. Since equation of computing PESC is complex and non-differential, gradient-based deep models cannot use PESC directly as objective functions. Lastly, signal to distortion ratio SDR, which is proposed by Fevert in 2005. In 2010, Khandokar et al. Proposed SDR as objective cost function. As our motivation, in 2006 by Weeks et al. And in 2011 by Emily et al. Show that optimizing with objective measures of success is not always optimal, since they do not always strongly correlate with subjective measures. In subjective evaluation, human listeners give relative preference scores on the quality of the speech. Average of these scores generate a mean opinion score, MOS, which represents human perception of the speech. In 2016, Petron et al. And in 2019, Aviala et al. Proposed human-assessed MOS estimation model separately. In 2020, Deng et al. Formulates another MOS estimation model which shows best human-assessed MOS estimation results in real-world environment. Therefore, for a good perceptual enhanced speech, good scores in objective functions and good scores in subjective evaluation are required. This leads to the idea of joint learning where multiple targets are optimized in the same time. CS speech estimation with other training targets are successful. For example, in 2018, Donahue et al. Performs speech recognition. In 2019, Lee et al. Estimate phase response. In 2020, Seliza Foster et al. Perform phoneme class, and Z et al. perform speaker identification. So we say that in a similar manner, joint learning of speech enhancement tasks and speech quality estimation can provide better speech quality acoustically and perceptually. Therefore, we propose a joint learning scheme that estimates speech quality MOS score and enhances the speech signal. MOS estimation model produce encoded embedding vectors that extracts perceptually useful features that are important for human-based assessment. Proposed speech enhancement model is conditioned on that embedding vectors and enhanced the noisy speech using a separate encoder-decoder framework. Our proposed model jointly updates both the MOS prediction and speech enhancement models during training using speech enhancement and MOS prediction loss terms. Now, problem formulation. In the time domain, noise the speech is a sum of clean speech and noise. In the time frequency domain, noisy speech is the multiplication of magnitude and exponent of phase. We can consider the noisy phase as a union of two sound sources, S, which is the clean speech, and N is the noise. Therefore, we want to approximate magnitude of clean speech by learning the function F on noisy speech. First part of our proposed approach is the automatic speech quality assessment model. We adopted a data-driven MOS prediction model proposed by Deng et al. In 2020. This MOS prediction model consists of an attention-based encoder-decoder structure that uses stacked pyramid bidirectional long short-term memory PBLSTM networks in the encoder. We denote this model as pyramid MOS or PMOS. The output of the PBLSTM node is an embedding vectors L, T, tau with H that is as defined, where epsilon is the direction factor between successive PBLSTM layers and L is the layer number. The encoder output is generated by converting the hidden states of the last PBLSTM layer into vector H. The P is the total number of final embedding vectors with index tau. The decoder of the PMOS model is implemented as an attention layer followed by a fully connected layer and output estimated MOS of input speech. Self-attention mechanism uses pyramid encoder output at the ith and kth timestamps to compute attention weights alpha PMOS and context vector C PMOS with the shown equation, where Q is the PMOS attention weight matrix. Now we design our attention-based speech enhancement model. Proposed speech enhancement model is also an encoder-decoder structure. We name it as AC model. AC encoder takes a single time frame of a noisy speech mixture MT as input, and multiple BLSTM layers are stacked together to create a hidden representation of the frame ZT. Then attention mechanism is applied using the mixture encoding from AC model G and P BLSTM encoding H from the MOS prediction model. We compute a score for each embedding vector H using a learnable weight matrix W. Attention weight for AC model alpha forms a context vector CT for each mixture frame. Prior computing CT, H passes through a linear layer L using following equation. Context vector and AC model embeddings vectors are concatenated and passed to the decoder module. Decoder consists of a linear layer of TNH activation function, two BLSTM layers, and a linear layer of REL. It outputs the estimated enhanced speech asset. Now, finally, we join these two modules together for joint learning. This is called AC plus PMOS model. Our joint learning objective functions uses a weighted average of signal approximation loss, LSA, the MSE of magnitude spectrum, LMSE, and the MSE of MOS estimation, LMOS. With hyperparameter lambda 1 and lambda 2, the overall loss function represents by L. We first train the PMOS model using LMOS. Then we train the AC model using lambda 1 equals to 1 while running the PMOS model in inference mode. Finally, we train both models jointly using L for further reduce any correlational difference between the true MOS and estimated MOS in the PMOS model and to increase perceptual quality of the enhanced speech. Now, dataset. We train and evaluate using cosine and voice speech corpora. Now, cosine contains 150 hours audio, which captures 7 channel variable microphones with multi-party conversational in a variety of noisy environments. For example, street cafeteria bus with noise etc. The approximated SNRs range from minus 10.1 to 11.4 dB. And voices records audio with 12 microphones placed in 2 rooms with different background noises to capture reverberant noisy speech. The approximated speech to reverberation ratio ranges from -4.9 to 4.3 dB. Most data are captured from the listening study that is outlined by Deng et al. 2020, which contains most quality rating of 18,000 cosine signals and 18,000 voice signals. Noisy and reverberant stimuli of both datasets are divided into training 70%, validation 10%, and testing 20% sets and trained separately. In experimental setup, PMOS encoder uses L equals to 3 PBL stem layers with 128, 64, and 32 nodes in each direction respectively, on top of a BDL stem layer of 256 nodes. The reduction factor epsilon equals to 2 is adapted here. Therefore, the final latent representation of each term is reduced in the time resolution of factor of 8. The context vector is passed to a fully controlled layer with 32 units. On the other hand, AC model uses a BLSTM layer-based encoder-decoder architecture, where encoder consists of two BLSTM layers. Each BLSTM layer contains 20 nodes and linear layer of 321 nodes. Input feature vector is the magnitude of the mixture spectrogram computed using a Hamming window of 50% overlap normalization. Now results. In table 1, we show the accuracy of our MOS estimation model. The parameter of metric performance are mean absolute error, MAE, root mean squared error, RMSE, Pearson's correlation coefficient, PCC, Pearson's rank correlation coefficient, SRCC. We compare with two MOS estimation models. One is NISQA, which is modified to estimate MOS using a CNN and BLSTM architecture, and the one is PMOS, which is trained without any joint learning. Results show that the proposed AC plus PMOS clearly outperforms other MOS prediction models according to all metrics. The absolute correlation error minimizes to 0.6 compared to the original PMOS approach. This justifies the use of our PMOS model and also points the benefit of joint learning. In table 2, we compare speech enhancement performance in several metrics, such as in PESC, scale invariant SDR, SISDR, extended STY, ESTY, and MOS LQO. MOS LQO is the predicted MOS score of the INTERSPEECH using our PMOS model. AC is our baseline, and we experiment with different MOS terms like MSE, MOS, SA, SDR, as mentioned before. With the MSE loss, we see improvement in objective scores, except MOS for the cosine data. We see that LMSE in SA maximizes the overall objective intelligibility, whereas LMOS focuses more on perceptual speech quality. With SDR loss, we observed an average gain in SISDR. However, it yields a poor score in other metrics. We compare our proposed approach against a generative adversarial network GAN, which individually optimizes the PESC and ESTY. We denote this model as metric GAN. Also, we compare against an ensemble-based approach named SSEMSE that uses QualityNet, which estimates PESC scores as their objective functions. Now, we calculate the performance of our proposed model using three combinations of loss functions. Using LMSE and LMSA, we achieved the highest SISDR scores for both corpora, though these results are nearly identical to the models trained with three loss items. Using the three loss terms, MOS scores are the highest results for all metrics. Metric GAN optimizes PESC and STY, hence it outperforms other models in terms of PESC and EOSTY separately, though the scores for our 2 and 3 terms AC PMOS approach are only slightly lower, even though PESC and STY are not considered during the training. The SSEMSE approach yields the lowest score across all the metrics. In figure 1, shows the average score of SISDR and ESTY performance of the different models as a function of SNR. Our AC plus PMOS approach outperforms all the other models at each SNR in SISDR. In the case of ESTY, metric GAN STY gives the best results. However, in high SNR conditions, our approach gives likewise performance. In conclusion, in our proposed speech enhancement model utilizes a speech quality MOS assessment metric in a joint learning manner. Results show that proposed AC plus PMOS model outperforms other models in different noise environments. However, we evaluate our model's subjective score using a MOS estimation model, which is not a true MOS. Our assessment model provides utterance level-based feedback, which may be suboptimal since the model's embeddings are calculated at the frame level. Here I conclude my presentation. Thank you all.